Okay, so we're going to finish up section 3 today, and we'll start on section 4. The test is next Wednesday on sections 2.3, 2.4, 3.1, and 3.2. And I'll post a review before the weekend. You can bring a cheat sheet like you have. Next Wednesday. So we're going to do one more truth table. We've done the truth table for this particular logic statement, and we did the truth table for this one. So I ended up making up another one that was a little harder than what we've done previously, just so we can have a little challenge. So this says, if not P or Q, then not Q and R. So we've got everything. We've got OR statements, we've got an AND statement, we've got negations, we've got if-then statements. So the first thing we have to do is figure out how many rows we need. So remember the rows. We had the choices of 7, 9, 17, and 33, I think it was. That's because they only depend upon the number of variables we have. So the question is number of rows. 17. And that's because, who answered that question? Jackson. 2 to the 4th power. Well, so how many variables do we have? 1, 2, 3. So we don't count this twice because one's a negation, so it's only 3. So the answer is 9, yeah. So it's going to be 9 rows. Yeah, because this is how many, the number of rows depends upon, you set up your first 3 columns of P, Q, and R, and you work on that pattern. So it doesn't, we'll need one when we do the columns, but for as far as the rows are concerned, it only depends upon the number of letters we have. So we have 2 to the 3rd power plus 1, which is 9. So we need 9 rows, and the number of columns. So we need at least 3 columns to put all the truths and falses in there, plus however many we need to represent this logic statement. So somebody, I think it was the other class, said, well, all you have to do is see how many times you see these the letters or the negation of the letters. So we have 1, 2, 3, 4, and then you have 1 for each logic symbol. Yeah, that's not a very good 9, but yeah, not sure why it looks like that. 9. So how many statements, Tim, or what do you think?
Would be 3 plus 7?
Yes, so the second one is 7. So we're going to need 10 columns. So let's go ahead and make up a table. So it's 9 rows by 10 columns. Okay, so I'm going to need 9, so I need 5. Okay, I've got to make it up with 4 little ones. So I'm going to make it that. So clone that. So there it is. So I think I'm going to have to put this on one page. It's too small. So let's see who we're going to ask. Yes, Justin.
Wait, where did you get the 7?
Okay, where did you get 7? Where? Well, Timber got it from 1, 2, 3, 4, 5, 6, 7. So there's 4 for the different letters or the negation of the letters. So this counts as 1. This counts as another. That counts as another. So there's 4 of those. Plus we have 3 logic symbols. So you get 4 plus 3 is 7. So we're going to fill out the columns, P, Q, R, and then we write our logic statement. Like that. So now I can move it up because I have everything. So let's start with somebody here. So Mary Jo. So what is what should I put in this first column? So we do half trues, half falses. Okay, Mackenzie. What do we do next? So you do them 2 at a time. And then, who am I going to pick next? Harmony. So what do I put in the R column? Yep, true, false, true, false, true, false, true, false. So Hayden, what's the purpose? What did I just accomplish by filling out these 3 columns? So what are all these different arrangements? Yeah, they're all the possible combinations of trues and falses I can get. So that's why we go through this first step, is just to list all possible combinations of trues and falses for each one of these statements. Okay, so now we're going to fill in these, and what I'm just going to ask you is the question: do I copy the same thing that's in these, or do I copy the opposite? Okay, so this column, Justin. Do I copy the same that's in this column or the opposite of what's in the column? Opposite, because they add a little symbol which means negation. Okay, so I'm going to, instead of 4 trues and 4 falses, I'm going to do 4 falses and 4 trues. Let's see here, Miranda. So why don't I do anything here yet? Yeah, so I have to have something over here before I can actually fill it out. Okay, so do I do the same or different? Same or opposite for the next one? So I'm going to ask same, yeah, because it's just Q. So we just copy over what's in column Q. So Melissa's back there. So what should I do here? Same or opposite? So I have this little squiggly thing. Opposite. So that means I should start with true or false? False, because this one's true, right? So you can do the same pattern. You just start out with the opposite truth value. Okay, and the last one obviously is the same, so I'm just going to do it. Same as column R. Okay, so that's easy, right? So you should be able to. There's no reason why you can't get at least this much right, because you could copy these down in your cheat sheet for this size, And here we're just either doing the same or opposite. So, okay, then we have to do, now that we have two truth values on either side of this operation, we have to fill these two columns in. So Laramie, what is the, do you remember the rule for the OR statement? That's the AND statement. It's the other one. Yeah, they have, for the OR statement, they both have to be false to be false. So tell me where I should enter false when I'm coming down here. Yep, right there. Oh, another one there. Okay, so those are the two cases. Get two falses. You can see the rest of them either have, they have one true somewhere in there. So we filled out the two falses, so the rest of them we can just stick in with trues. Okay, who am I going to pick now? Harley. What's the rule for the AND statement? Okay, so tell me when to stop. Right there. Yeah, okay, so we have two out of the 8. All the other ones are false, so we can put falses in there. So now we have one less thing to do, which is use the if-then statement to apply. And so we use the last thing, we compare these two columns. Somebody asked me yesterday, can we use colored pencils during the test so I can keep myself straight? And the answer is yes, if you want to use colored pencils, so that helps. So then the final thing we have the if-then statement, which has the rule. So let's see, who am I going to ask? Caitlin. So do you remember the rule? There's one case where the if-then statement is false. Do you remember which one that is? Yeah, when is the if-then statement false? Just, yeah, so when it's true, the first statement is true, and the second statement is false. Again, that's because the truth statement would be the thing that I'm saying you have to satisfy, and the false statement would be the reward. So if you don't get what I promised, you're not too happy. So we look down through here, and we got to make sure if you have to use your fingers to keep them straight, which I can do on my computer screen. So what I'm looking for is true for the first one and false for the second one. So we'll look through them, and I find quite a few, don't I? There's actually 5. I found 5 of them. Do you see 5 of them? Yeah. So this one is true false, so that's false. This one's true false, so that's false. You can ignore these ones. Anytime you have a false for the first one, it doesn't count. This one's true false. Oh, over here. See, I'm almost missing it myself again. True. Okay. Let's see. I've got to put my fingers back up on here. So I got true false is false, true true, true false. So 5 out of the 8 were false, and so the rest are true. And that's the answer right there. That's the final answer. If you can get, just filling in the numbers, you're going to get at least more than half credit. So hopefully that's becoming fairly easy, reasonably easy. Is everybody finished with that? Does anybody need me to? Okay, we talked about this negation. The negation of the if-then statement, we proved that these statements were the same because we generated the truth tables, and then we compared the final answer, and they matched, so we knew that was true. There's also another equivalent statement. So the equivalent statement of the if-then statement, not the negation of the if-then statement, but just the if-then statement, is equivalent to the negation of P or Q. And we already know what the truth table looks like for this because we've just talked about it. So remember, the truth table for this was true, false, true, true. That's because the first two columns, we have true, true, we have true false, we have false true, and we have false false. So if I make a truth table up, the truth table for the if-then statement is the only time the if-then statement is false is if the first statement is true and the second statement is false. So that's the truth table for that statement, the one that so let's do the one below. And it's going to take 5 by 5, 2 columns for the P and Q, and then 1, 2, 3 columns for the statement. So we fill out the first 2 columns. We do again, you can write this down if you don't know what you're doing, but we alternate. We do 2 at a time, then we alternate. Then we go to the columns that involve the letters. This is the negation, so we do the opposite of the column that we already have written down. And the Q is just a copy. And then we apply the OR statement. The OR statement is false only if they're both false. So we compare these 2 columns and we see that this one is the only case where they're both false. This one's true, this one's true, this one's true. And if we compare that with this, you see they're the same thing. So they are equivalent to each other. So let's just, we could use the statement we just did previously, and we could do the equivalent statement that doesn't involve if-then. So I think the original statement was if that is an authentic Rolex watch, then what was it? I'll be surprised. Then I'll be surprised. Okay, so that was then I'll be surprised. So an equivalent statement would be that is not, so I'm making it a negation, that is not an authentic Rolex watch or I'll be surprised. So those 2 statements should be equivalent to each other. I think they are. So okay. That's another example. We're not going to do that one. Yeah, why don't you? We'll let you do this one. So I'm going to let you fill out the truth tables. So there'll be two truth tables. So they'll both be 5 by 5, and see what the answer is, and then if they're the same, then they're equivalent. If they're not the same, they're not equivalent. So I'll give you a little head start so you can start working on them. I got to set a timer because I always say I'm going to wait and then I don't wait long enough. I have no self-control. Did anybody watch the debate last night? I had a hard time watching that. Tim Kaine was painful. He was. It started out bad because they didn't answer the first question. You know, the first question, and they start going off on their prepared speeches. It irritated me. The question was, what makes you qualified to take over the presidency if something would happen to the president? Yeah, I'm much more confident than the guy. Yeah, so I didn't. Yeah, I think you always wonder at what point when you start making comments like that. My brother made the same comment. when the Secret Service starts to come and investigate you, you know, you're making threats to the president. Yeah, I kept turning it on and off. I couldn't. Tim Kaine was wound up too much. Some people said the strategy was that Tim Kaine wanted to get Pence either to not agree with Donald Trump or to say Donald Trump never said it, and then have a commercial that shows him saying he didn't say this, and then showing him saying that he didn't say that. That's the one worked out. They've already got a commercial that shows that Donald Trump. That's ridiculous. We never said that. And then it goes. He says it. She has. I mean, TTP is one of them, and I don't really know enough about TTP. Does anybody know what TTP stands for? Oh, because I'm going to tell you. Oh, we're done. Trans-Pacific Partnership. It's the trade. It's the equivalent. There's what's called NAFTA, which is North American Free Trade Agreement, and then there's TPP, which is Trans-Pacific Partnership, and it's a treaty. And Clinton originally, when she was in the Obama administration, she supported it. But then again, it's hard to be part of an administration and not go along with the president. So whether she, which I could question. I don't think it's changed that much. I think if you just say, I'm a member of the administration, you're supposed to show unity, and I said, okay, I go along with it, that would be one excuse, which is reasonable. But, yeah, anyway. As they say on TV, most people don't think about this as much as I. There's people who get into it for whatever reason. I find it more interesting than some of this stuff on regular TV, so it's kind of entertaining to me. Okay, so those are the two tables, what they should look like. And then you fill out the first two columns just like we've been doing. So if you do this well, you're going to get one of the problems right on the test, because it's going to be just like, not exactly, but close enough that you'll get it right. Okay. So yeah, everybody following me so far? Everybody got this part? Okay. Next part, again, should be pretty easy. How about that? Everybody good there too? Nobody's okay. Then if-then statement. This is the only one that's false. All the others are true. And the or statement is false only when they're both false. So this is false. That's true. That's true. That's true. Hey, so these are the same. So if I ask you this question, are these equivalent statements? You would say yes. They are equivalent statements because the final truth values are the same. Don't assume I'm giving you one that is equivalent. It just turns out that this is equivalent. So, one way you could use this is if you wanted to reword something that, involved slightly different words but had the same meaning. So in the book, and I'm not going to ask, we're not going to use this, I'm not going to ask you to memorize them, but I'm just going to talk about them. Here are some other equivalent statements. They're equivalent because they have three little horizontal lines here. So the truth value that you would get from this would be the same as the truth value you get from this. I don't know what they are, but they're the same. You also have this where you have some kind of statement, and if you say or with just something that's always true, then the result of the or statement is true. If you have a statement, no matter what it is, if you have an and with a false, that makes it false. And let's see, a statement in union with the negation is always true, whereas the statement with the and for the negation is false, because this is something, this is not something. So if you try, there's no overlap between something being true and something being false. They're completely separate. Okay, and it says for simplifying circuits. So we're going to talk about circuits right now. So the last part of this section is looking at electric circuits and realizing that they can model logic statements in terms of ands or ors. So what we're going to do is we're going to look at two kinds of circuits, one called series. And series circuits are things that are connected one end to the other. Like USB, what does the S stand for in USB? Stands for serial, okay? In the old days, computers used to have what was called a parallel port. Does anybody remember that at all? Okay, so you used to have a serial port and a parallel port. The serial port is something where you connect one thing to another, and then you can connect that thing to another and connect that straight to another. Whereas parallel, you would take, usually the parallel connector was wider, and so you could take the first two things to one, and the second two to another one, and the third two to another thing. And when they used to send it to a printer, most printers back in the old days used to be parallel port. And so they would send, instead of sending the data one bit after another, they would send the information along 8 different wires. So if say it had 8 bits of information, instead of sending 8 bits in a row and interpret it, they would send 8 bits in separate cables. So the series is showing these switches connected end to end, and the parallel switches, the circuit, these are wires, these represent wires. A wire comes in, it breaks off into 2 wires. One goes to one switch, the other break off goes to the other switch, and then they come back together and go like that. Obviously parallel, 2 parallel lines look like this, so that's how you remember parallel. Series, you just have to know they're connected in a line. Okay, so let's look at the serial case first. There are four different configurations we can have. We can have, so this is this line. We can have the switch closed. So I'm going to start with the switch closed. So that's, I pull that down, I close my switch. Then I have my piece of wire, and then I have another switch that is also closed. So this is a switch, and this is a closed switch. And this is another closed switch. It's just like a light switch. Okay. And the question is, does current, which is electrons, does current flow? Question mark. Well, it does, because you've connected all these wires together. When you connect, when we turn the switch here from off, right now the switch is open, so the electricity can't flow, so the light's off. You turn the switch on, closes the switch so that you do have a path for the electrons to flow. And so in a series, you have to have, in this case, when they're both closed, the electricity flows. It has a path. So the answer is yes. And we're going to do the same thing for the other 4 cases. So let's say the first switch is open, second switch is closed. So this one's open. I'm not going to write switch. I'm just going to write open, closed. Ask the question, does current flow? Question mark. The answer is no, because it gets to here and it doesn't have anywhere to go. If I have the first switch closed and the second switch open, does current flow? The answer is no. And then the final case is where they're both open. And does current flow? Well, it doesn't flow any less because it just doesn't flow. So the answer is no. And so you can make up a table using this information. So let's set up a table. And it's going to be a 5 by 5 table. Surprise, surprise. So actually, it doesn't have to be that big. It's going to be a 3 by 5. 3 by 5. Okay. So first, column 1 is switch 1, which is the first switch. Okay. And then you have switch 2, and you have current. So the first case, closed, current flow, yes. The second one is open, closed, current flow, no. This is 1 and this is 2, from left to right. So this one, switch 1 is open, switch 2 is closed. Does the current flow? No. This third one is switch 1 is closed, switch 2 is open. Does current flow? No. And finally, if they're both open, does current flow? No. Well, that should look kind of familiar. If I say this is a closed switch is true and an open switch is false, I'll get true, 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 false, false, true, and false, false. So that's kind of the equivalent to the switch open, closed is true, false. And whether current flows is going to be the result, which is if yes is current flowing is true and no current flowing is false, then I get true, false, false, false. So what we can say is we can say serial or series, not serial, but series switches, series switches is analogous, and now how do you spell analogous? Not like that. Something's wrong. Anyway, it doesn't matter. Is analogous to the AND statement. And you can do the same thing for the other circuit, for the parallel circuit. And what you'll find out is that, well, let's go back to the parallel circuit here. If they're both open, no current flows. If I close this switch, then current flows to the top but not through the bottom. So I'm still getting current flowing. If this one's open and I close this one, current will flow through the bottom one. And if they're both closed, then it'll flow through the bottom and the top. But just looking at it from a current flowing versus current not flowing, it would behave like a OR statement, a logic OR statement. So I'm going to switch to my computer, to my browser here. So this is under Logic Gate in Wikipedia. And what we have is we have the corresponding electric circuits and the truth tables associated with those kinds of circuits. So if you have, this is called an AND gate, and instead of trues and falses, we have 1 volt or 5 volts, whatever your system is based on, voltage versus 0 voltage. So a lot of times it's 5 volts, sometimes it's 3.3 volts. So this would be like not necessarily, well, it would be switches, but the switch would be controlled by the voltage. So if the voltage is 1, the switch is closed, and if the voltage is 0, the switch is open. So it's equivalent to switches. It's just on a small scale. So you can see the truth table is upside down because we have true is true, false is false, false true is false. So that's called an AND gate. Then you have the OR gate, which looks like that. And again, it's upside down, but it's, true is true false is true is true, false is false. And then you have NOT, which is the negation. So the negation thing looks like this. It says it is more commonly called an inverter. So we'd have an AND gate, an OR gate, and an inverter. We wouldn't probably say a NOT gate. And there are actually some other circuits that you have to play with. You have a NAND gate, which means not AND, so it's exactly the opposite. 2 trues make a false, and everything else is true. You have a NOR gate, so it's not OR. So again, the only time a NOR gate is true is when they're both false. So it's the opposite. And then you have an XOR gate. I'm not sure exactly how you pronounce that, and it looks like this one here. So that's that looks very familiar to me, because that is kind of when we were doing binary addition. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0, and then you'd have to have a carry. So you probably use this kind of gate a lot in computer circuits that add numbers, add binary numbers. Plus there's another thing you got to stick on there, which is the carry part of the whole thing. So let's just click on one of these specific. So this is, let me pick that one out. So this is actually what the AND gate would look like. So this is the electric circuit. These R's stand for resistance. So they're little elements that control the amount of flow of electrons. And these, does anybody know what those are? What those symbols represent? The ones right here and there, they're the same thing. Okay, if you don't know, I don't expect you to know. So, see, you'll learn something today. Not only what was the thing we were talking about, what TPP was. So not only know what TPP is, those are called transistors. Okay, and transistors are just microscopic switches. So what happens is that when you apply 0 voltage to this thing, the switch stays closed. And notice these are in series. So this is switch. This is the first switch, and this is the second switch. And what we're looking for is current to flow through these two switches and give us some output. So when the voltage to this transistor is 0, the switch is off. When the voltage to this transistor is 5 volts or some level, it turns the switch on. But there's no mechanical switch. It's all electronic switch. So the only way for voltage to flow through both of these switches is if they're both on. So if you have a voltage applied here and a voltage applied here, rather than 0 volts, it turns both of the switches on and lets the current flow through the thing. So that's all an AND gate is. So notice that they're basically two electronic switches that are in series with each other, just like we looked at. And if we go back and we click on the OR button here, so it looks like it's the same thing, but notice that this feeds voltage in here and it feeds voltage in there, so it's different. You have this extra connection and this extra connection. This, in a series, you go straight from here to here. And as a consequence, these two switches are in parallel instead of in series, and therefore it behaves like an OR gate. Let's see what, I haven't done this before, so let's see what one of these other ones look like. The NAND gate. That's interesting. I'm not exactly sure I know what that means. Anyway, it's more complicated. Pardon me? Yeah, I mean, you've got two transistors, but I'm not sure what you've got two connections here, so I don't really know what that means. That must be the input, but I'm not sure how it must be a special kind of transistor. Anyway, so that's kind of, so what we're going to do here is we're going to do two things. We're going to, and luckily I don't test you on this, so you just have to do the homework. There's two things. You can take a set of electric switches and convert them into an equivalent logic statement, which is what we're going to do first. And secondly, you can take a logic statement and create the circuit. So this one says, write the logic statement representing this circuit. So you see we've got these two that are in parallel. Was it the AND or the OR that we said was the parallel thing? What's that? OR. Yeah, it's the OR. So these two letters represent the statements. These switches represent the statements where closed is true and open is false. So we don't really have to worry about whether it's open or closed. We're just saying that these two switches, which are equivalent to statements being true or false, are in parallel. So we're going to use an OR statement to connect these two in our logic. Then we have this part connected end to end with this. So this switch is in parallel, is in series with this whole thing. So the answer is, the way we would do it is we'd start with the parallel thing, and we'd say we have either R or Q or Q or R. It doesn't matter. The order is not important. So I'll do it in alphabetical order. So it's going to be Q or R for that part of the switch. And then that is connected to the P switch. But because the P is in parallel, or is in series with this switch, we would put an AND right there. And we could put little parentheses. So that's the equivalent logic. This is the equivalent switch arrangement for this logic statement, which would be P or Q, pardon me, P and Q or R. Now, did you notice any logic things that said if then? You know, when we were showing that? We didn't, right? So there may not be there may not be a equivalent electric circuit for if-then statements. But if we go back, remember these equivalent statements we did? We said the equivalent statement for if-then is not P or Q. So that would be a case where we might want to use this equivalency to be able to construct an electric circuit that would answer the logic question if P then Q. We could use this instead because it has the same result. I just realized that. Just thought about that. Okay, so you got a couple like that. You can watch the videos and try to understand it as much as you can. And then the second case is we have, so we'd say P and Q or not P and not Q. So the question is, how do we create a circuit that looks like that? The negation stuff we haven't talked about. I'm just going to explain what you would do. Like I said, I just want you to have experienced it. I'm not going to quiz you on it. So let me just explain how this works. They're not. Actually, they're never going to be on the test. So try to stay awake a little bit. Okay. Okay. What's that? Yeah, you're living. There you go. It's good. It's we should all know a little bit about something. And actually, it is good, you know, from a lecture system standpoint. You ever think about, you have the rooms where, you know, you turn the switch on one way, on and off one way, but then you go to the other switch and it, you know, the opposite, it changes depending upon which way it is. And so that's the same kind of, that's what electricians learn how to do. How do I wire the things up so that when I turn this one on, that, you know, it's not always up is not always on. It depends what the other switch does. Whether they actually understand how it works or whether they just memorize that this is the way I need to wire it up, it doesn't, you know, they don't, so it works. That's what you care about. Okay, so the first thing is we have this OR statement here. So this is going to be, OR is parallel. So I'm going to draw my circuit. I'm going to take it, I'm going to break it up into a P switch and a Q switch, like that. So this is P, and this is Q. And then they come back together. And because this is in series with that, because there's an AND statement. So this AND statement means that I connect this to that, but straight through. So I take the wire and then I break it apart again. Actually, no, I wouldn't do that. Hold on just a second. So this is also in series. So I would connect this first one up. Now, how do I handle not P? Well, what you would have to do, you'd have to design the circuit so when these are open, these are closed. And when these are closed, this one's open. So I'm going to show them as closed to show how you would do the negation. So this would be not P, and this would be not Q. So when this would close, this would open. And when this closes, that would open. And you can design circuits to do that, but that's how you would do it if you had this problem to solve. Like I said, I don't want to spend, you know, days making sure you know how to do these things. I want you to just kind of get the general idea of what's going on. So, you know, 2 years from now, what hopefully you can remember is that logic can be represented by logic statements can be represented by open and closed switches, and those switches in computers are transistors. And you can do all kinds of amazing stuff with computers just by opening and closing switches. Again, that's why autonomous cars worry me, because you think about it, opening and closing switches seems like you couldn't do that, but you can. Okay, yeah, this is my. Pardon me? The autonomous cars? I think some of them are. That's why they're concerned about. Yeah, no, because you wouldn't want to get a Wi-Fi range or you'd be in trouble. That's actually, there's been airplane crashes, and they're flying places where there isn't any Wi-Fi. So the newer planes have things that will connect to satellites, but they don't continuously connect to satellites. Just the reason that you get on Wi-Fi here, so your bill doesn't go up using your data. Same thing for airplanes. They don't continuously talk from the airplane to the wherever it is. But the problem is if the plane crashes, you don't know exactly. Sometimes you don't know exactly where it is, like that. Oh, yeah. I mean, there are security issues associated with it. There was something else that was recently they were talking about where they could hack into something that you wouldn't have thought about. I can't remember. That might have been it. Yeah, things crazy like that. Yeah, hack somebody's pacemaker. That would be crazy. Okay. Anyway, I'm going to skip over that one. So there's your homework for section 3. So that's due next Wednesday. So that's also the day the test is, so don't wait till the last minute. I wonder what they do. I haven't looked at this. You do it for the first time, you write down your notes, and then you forget what the book actually says. So while you're copying those problems down, I'm going to see how they handle this negation thing. Oh, they don't actually, they just show it as negation. They don't have a difference in the switch settings, but oh, there was something I was going to tell you. What was it? Wednesday. So do we have any Disney fans in here? Okay, so here's a line from a Disney show or book. I'm looking for my father. He's not crazy. He's a genius. What's that? Beauty and the Beast. So here's the text from my daughter Jennifer. Here's the conversation that just happened here. Clara is in her crib looking through the rails. They're still in their cribs, luckily, because they haven't had to buy a new thing. So Jennifer, my daughter, says, "What are you looking for, Clara?" Clara says, "I'm looking for my father. He's not crazy. He's a genius." 3 years old. So that would be weird, except it's a direct quote from Beauty and the Beast. It's still hilarious. That would be funny. Yeah, it is cute. So here's another, my grandson, Xander. We went up this weekend, and we had he's interested in, like a normal boy, he's interested in buses and trains and airplanes. And so we have this Fisher-Price airplane. And did anybody ever have a Fisher-Price airplane? Did you buy one? Let me show you the picture of it's probably what they would call vintage now. So let's go to eBay. Vintage Fisher-Price airport. There it is. Ours doesn't look, the airplane looks kind of like that. Anyway, so we took it up. And so Heather calls last night. She goes, "I wanted to tell you, after dinner, Xander went in the other room. He's 18 months old, and he goes, I love you, airport. Or airport, I love you. So he likes his airport. Or airplane. I guess it's airplane. Okay. So we're going to move on to section 4 now. I'm actually a little ahead of the group last year, so I'm not sure what that means. So we have, well, we've already talked about the conditional, which is the if-then statement. You probably remember this from, you may remember this from geometry. You remember there was things called the converse, the inverse, and the contrapositive. You guys remember that? You hated geometry? Yeah. What's that? Yes. It might have been. I'm not sure if I. Yeah, I can't remember whether I showed it to you or not, but I didn't think I got that far, so maybe I did. I might have skipped. I skipped ahead and gave it to you. Yeah. Okay. Yeah, I couldn't remember what it. Okay, so so we're going to look at those things, but we're going to look at them from a logic truth table standpoint. So the conditional, remember, you should remember because we just talked about it. The conditional is the if-then statement. There are 3 other statements that relate to either switching the antecedent and the consequent, which means the first term and the second term, or making them negations of each other. So you may have remembered those from geometry, but you may not have used negation or. So if this is the if-then statement, the original if-then statement, if P then Q, the converse is you switch the Q and the P. So it's going to be if Q then P. In the inverse, you keep the order, but you make them both negations. So it would be not P, if not P, then not Q. And then the contrapositive is you switch them and make them both negations. So it would be if not Q, then not P. Now some of these are equivalent to each other, so they work all the time. Some of them work some of the time, but not all of the time. If you make a truth table up and they get the same values, the same final results, then they are equivalent and therefore they're the same all the time. So we can prove that whether they are the same all the time by using truth tables. And they're fairly easy ones to do because there are only 2 statements and the actual logic statements are pretty simple. And I think in the book they show you what they are, so I think I'm going to show you the result instead of going through them. So it's not on this page. Anyway, this is in your book as well, which is basically just what I wrote down here, so you don't have to do that again. It turns out if the conditional statement is true, then the converse and inverse may be true, or might be true, but they're not always true. A lot of people try to use that as logic. Like if that animal has feathers, then that animal is a bird. The opposite the converse would be if that animal is a bird, then that animal has feathers, which in most cases is true. If you see an animal that has feathers, it's most likely a bird. I can't think of any right now where you have an animal that are there any animals that have feathers that are not birds? Yeah. So but maybe the original one wasn't true either. That's if that animal is a bird that has feathers, you could have a bald feather. I mean, you could have a bald bird with no feathers, right? Somebody Bing, maybe we have somebody who can think of, oh, Katie Lee left. Okay, that's what it was. Anyway, so sometimes you have statements which are the converse is true, but you can't guarantee that they're true. The contrapositive is definitely true. If the original conditional statement is true, then the contrapositive is definitely true. So here's what I was referring to. This is in your book, so it's on page 111. So this is the first two columns, which are all the truth values. And here are the four different choices, just the standard conditional, which is only false if the first one's true and the second one's false. If you do the truth table for this, you'll get true, true, false, false, which is not exactly the same. You have the inverse, not P, if not P, then not Q. You get true, true, false, true, which is not the same as this one, but it is the same as the converse. And the contrapositive, if you did the truth table for the contrapositive, you get true, false, true, true, which is the same as the conditional. So that's why you can make the statement that if the conditional is true, then the contrapositive is always true. And if the converse is true, then the inverse is true as well. So let me let's see if I've got an example somewhere here. So that they are equivalent because the final truth values are the same between the two. So I think I've got some examples here. Okay. Given the following statement, birds of a feather flock together, what are the inverse, the converse, and the contrapositive? So you got to do this for a couple of homework problems. So the if-then statement is the original statement. So the converse would be if one is a bird of a feather. Oh, sorry. So actually what we need to do first is make this into an if-then statement. Okay. So it's easier. So we'll say if one is a bird of a feather, then one flocks together. Again, I don't want to use if I'm a bird because I'm not going to be a bird. So I have to be general. If one is a bird of a feather, then one flocks together. So that's the equivalent if-then statement coming from the original statement. Okay, now that we have the if-then statement, we can construct the other statements. So the converse would be if one flocks together. So let me write out converse. If one flocks together, so it's kind of what I just talked about with the bird thing. If one flocks together, then one is a bird of a feather. Are there any animals that are not birds that are in flocks? Yeah, but there could be. That's what you have to be careful. You don't know whether there are people that are animals that are not birds that are called flocks, but it turns out there must not be. Okay, if one flocks together, then one is a bird. So that's the converse. The inverse would use the same order, but you would change them to negations. So if one is not a bird of a feather, then one does not flock together. Again, if you had an animal that flocked, then other than a bird, then that wouldn't be true. So that's the inverse, and then you have the contrapositive, which would say if one, so we just take the converse and we make it, if one does not flock together, then one is not a bird of a feather. So that's the contrapositive. So if all so the first one was if one is a bird of a feather, then one flocks together. That means that if one doesn't flock, then one isn't a bird. Even if there were other animals that flocked besides birds, that statement would still be true if the initial one is true. So that's kind of the way it works. So those are the other logic statements that are related to the conditional statement. The conditional statement being the if-then statement, where you change things around, order or negations, make them both negations. So what might you have to do relative to a test is if I gave you a statement, you'd have to write what the inverse, the converse, and the contrapositive would be. So if you were putting it down in your notes, I might just write what they are. You know, converse is if Q then P, and the inverse is if not P then not Q, and then you could just put it in there. So that's kind of what we're looking for. And we just talked about that, so we don't need to. A conditional statement and its contrapositive are equivalent, and also the converse and inverse are equivalent. So don't write that down. We already talked about it. This is just some common translations of the if-then statement, which are equivalent to if-then statements. And I sort of used that when I was doing this problem. I had to take the original statement, which was not an if-then statement, and I created it into an if-then statement. But there are other things that you could use, other ways you could mean the same thing as an if-then statement. So if P then Q, that's what we start out with. We might start out with if P, comma Q. We leave out then a lot. We've seen that before. Sometimes you leave out the comma. P implies Q. P only if Q. P is sufficient for Q. We wouldn't normally say this. Those are more math things, right? So we're already a little bit ahead of the other class, so I'm going to stop there so I don't get too far ahead of the other, or too much out of sync. I remember hearing it. What is it called? I have heard it, but I can't remember it. A what? A murder? Okay. What's it called? Kindness? Oh, okay. Okay. So